So last time we started talking about extremal graph theory, and we proved Mantel's theorem, I think 4 times, which said that a graph with no triangle can have at most n squared over 4 edges. And actually, we even showed how we could prove a stronger statement, that stronger statement being that the unique graph with the maximum number of edges and no triangle is a complete bipartite graph where both classes are of size about n-half. If n is odd, you round one down and you round the other up. Otherwise, they're both of size n-half. So today I want to prove Turan's theorem. Turan's theorem. This is from 1941. And this is just a direct generalization of Mantel's theorem, where instead of maximizing edges with no triangle, we say that there's no clique on k plus 1 vertices. A triangle is a clique, but there are larger cliques as well. Okay. So the maximum number of edges in an n vertex graph with no k plus 1 clique. Okay. Remember, this means a k plus 1 clique is a subgraph. So no, this is a, let's see, all right, complete graph. The complete graph k plus 1. So the k plus 1 vertex complete graph is what a k plus 1 clique is. It's just a different notation. Is at most the following quantity: 1 minus 1 over k times n squared over 2. Okay. We're going to give a couple proofs of this, but I want to talk about this bound for a second here. What's kind of going on? Why have I written it this form? In other textbooks, you may see slightly different forms and so on. So what I want to look at here is just ignore the 1 minus 1 over k part for a second here. And then the upper bound is written, says n squared over 2. Well, n squared over 2 is basically the same as n choose 2, at least for n large. N squared over 2 is a little bit bigger than n choose 2, right? N choose 2 is n times n minus 1 over 2. So this number is a little bit bigger. But what I want you to think about is that n squared over 2 is approximately the most edges you can have in an n vertex graph, right? With no restrictions. If you just put down all the edges, you have about n choose 2 many edges possible there. Okay. Actually, you can rewrite this bound with an n choose 2 there instead. We just have to do some tweaks later on. And then we have this multiplicative factor in front of it that says, well, the maximum isn't n choose 2 because we've made a restriction that there's no k plus 1 clique. And what does that restriction do? Well, of the total, like 100% of the edges, it subtracts off 1 over k proportion of the total edges. Okay. So if you think about this for a second, what's going on is k gets bigger and bigger and bigger and bigger. So I'm forbidding a larger and larger and larger clique. So k10 versus forbidding a k100 versus forbidding a k1000. I'm allowing myself to get closer and closer and closer to just having all of the edges. But that makes sense, right? Forbidding a triangle is more restrictive than forbidding a k5, right? Because if you don't have a triangle, you don't have a larger clique, right? Smaller cliques, the absence of a triangle forbids a k4, a k5, a k6, a k7. But forbidding a k100, you could have smaller cliques in there, okay? So it's just to get a notion here in your head about how this sort of function here, well, actually the real function is the maximum number of edges, right? This is some hidden number here, how it depends on the k in the k plus in this quantity here. So the larger clique you forbid, the less restrictive, and therefore the more edges that you can have here. Okay, so that's why I like to write it in this form here, so you can see how it's tending towards this quantity here. Okay. And just to check a couple of things here, when k equals 1, we're saying that there's no k2, there's no 2 clique, which is a single edge, right? And then that's when k is 1, when k is 1, k plus 1 is 2, so no edge. And then this upper bound becomes 0, which is good. That at least like as a little sanity check makes sense, right? If you have no edges, then the maximum number of edges is 0. Fine. If k equals 2, then this says no triangles, right? Keep in mind k is off by 1 by the number of cliques here, so no triangles. And then this upper bound gives 1 minus 1/2 times n squared over 2. You get n squared over 4 together. And then again, you can always round that down. That gives Mantel's theorem back. right? Mantel's theorem is hidden here. So, and this gives Mantel's. Right? But this works for larger cliques, for K4, K5, and so on and so forth. Okay, so I want to start off like we did with Mantel's theorem and say, okay, we've got this bound. How close is it to the truth? Right? So I never have more edges than this, but maybe I can't get graphs with approximately this many edges and no clique. Right? We've seen instances of like Brooks' theorem, for instance, that Brooks' theorem says, hey, you can't have basically more than delta colors that you need, but sometimes there are graphs with many fewer. Okay, so I want to construct for you a graph that has no clique of size k+1, has n vertices, and basically has this many edges. Okay, it's not going to be exact, and you'll see why, but we'll get a more exact result a little bit later. Okay, so the question is it sharp? Okay, so is the bound sharp? That means like, is there any chance for this bound to be improved? And the answer is no, and here's why. So consider the Turan graph. So I'm defining this now, and it's denoted T sub kn. Okay, so the Turan graph has two parameters, k and n, and that is the n vertex graph with k vertex classes, each of which is an independent set. Okay. When I say k vertex classes, I mean that I can partition the vertices into k sets. Okay, so all the vertices are partitioned into k sets. Each of those k sets, not of size k many sets, is independent, and all edges are present between, I'll draw a picture and it'll be perfectly clear, two classes, and all classes are of size as close as possible. Which sounds very informal, but actually this is perfectly well defined. I'll explain here in a moment here. Okay, actually let's just say what that means. There are n vertices, and I split them into k groups, and I want those groups to be of size as equal as possible. So the sizes should be approximately n over k, but n might not be divisible by k, so each of the classes will be of size n over k ceiling or n over k floor. Okay, and how many of size n over k ceiling do you need? You need exactly the remainder of n divided by k, right? That'll just give you the additional plus ones. Yes, Van. This is literally a complete k-partite graph with classes of size balanced as close as possible. I don't think I've actually defined that term in the class, so that's why I've gone through this very, very like carefully here. But absolutely. So let me add this here, as Van points out. So this is what we call a complete balanced k-partite n vertex graph. Right? And each of these terms describes something that's going on. Complete means all the vertices go between pairs of classes. Balanced means the classes are of size as close as possible, so they're n over k floor and ceiling. K-partite means k partition classes. And also it means that the classes are independent, right? We know what bipartite is. That's two classes with all edges between and no edges inside. K-partite is just three classes. K classes, right? So let's just look at a couple pictures real quick here. Right, so the Turán graph T2n is just a balanced bipartite graph. Right, it's two classes here with all edges between, and this has size n over 2, and this has size n over 2. I'll say ceiling and floor. This works whether n is odd or even. Okay, then T3n is three classes, and they should be as close in size as possible. Right, and all edges are between. Now here I'm just going to write n over 3 for each of these, because if you're careful here and think about this for a moment here, there's only one of these. There's only one T2n, right? But T3n, depending on n, there's a couple of varieties here, right? All three classes might be of the same size. I might have one class that has one extra vertex. I might have two classes that have one extra vertex, right? It just simply depending on the divisibility of n there by 3, okay? Although for a fixed n and fixed k here, there's exactly one of these graphs, right? There's only one way to try and get them as close as possible. It depends on the remainder. So that little subtlety about divisibility there is sort of the reason why, at least for now, I'm not going to write a better bound than this one here, because the truth is like, well, whatever the number of edges in this Turán graph is. And so like you get, it's not exactly this quantity here. It depends on divisibility, and that's just ugly to deal with. Okay. So what we'll pretend for at least the first proof here, essentially, or just keep in the back of your mind, is just pretend that n is divisible by k and that the classes are all of size n over k. If you add one more vertex to that picture, it doesn't change the situation too much. Because actually, I didn't emphasize this when talking about Mantel's theorem, but in extremal graph theory, we tend, when we think about theorems like this here, we tend to think as n is approaching infinity. We like to think of this function, the maximum number of edges, as a function of n. So as n gets larger and larger and larger, we're thinking about this as a function, and sometimes we'll even divide this function by n squared over 2 or by n choose 2, and think of this as like a density, right? Like how many edges are there as a proportion of the total that could be there. And that proportion would just be this constant right here, right? The n squared over 2 would vanish when you take the limit to n over n choose 2, and it just spit out this integer, or not this integer, this rational number. Okay, but we're not going to think about it that way. It's just to tell you what's going on here. There's a lot of imprecision typically in extremal graph theory. A lot of our answers are approximate or asymptotic very frequently. Okay, so that's what the Turán graph is. So as Van points out, this will usually be described just simply as a complete k-partite graph in both of the textbooks. But when talking about in extremal graph theory, this has this special name. It's called the Turán graph. This is a super important graph. Although this is definitely a fancier, well, I don't know if this is a fancier name than complete balanced k-partite n-vertex graph, but this one is very descriptive. This is just named after someone, but yeah, okay. All right, so fine. That's the Turán graph, but what about the Turán graph? We didn't do anything with it. So let's examine TKN, okay? And make the following observation. Okay, it has no k+1 clique. Can someone tell me why there's no k+1 clique in TKN? It's easy, but it's a nice observation to make.
I think it's like you can do a pigeonhole argument, like there's only k, parts and no two, vertices in a single part share an edge. So you assume there is and then show it down.
Exactly. Van's got it exactly, right? So there's no k+1 clique because TKN has k parts, right? Let's say for a moment here, k is 5. And a k+1 clique has 6 vertices. So its 6 vertices are distributed among these 5 classes. So it's got 2 vertices in the same class by pigeonhole principle. But those 2 vertices don't have an edge between them because they're in the same class, which is an independent set, right? Maybe I didn't emphasize enough here. These sets are independent. There's no edges inside, right? And so that you can't have a k+1 clique, right? You need edges between all k+1 vertices. So it just doesn't fit, right? So for instance, this one is triangle free, right? Because if I had it, we actually saw this last lecture, but if this had a triangle, it'd have 2 of the vertices on one side. Well, there's no edge there. This one is k4 free because those 4 vertices of a k4, 2 have to be in the same class. I don't know which class, but they have to be in the same 2, and there's no edge between those. So it could be k4 free. And this is k6 free and so on, okay? So it has no k+1 clique. Great, so we constructed a graph with no k+1 clique. How many edges? Okay, number of edges in the Turán graph. It's about, let's for the moment just suppose n is divisible by k. Otherwise we get floors and ceilings, although it's not hard to determine what the exact answer is. Well, how many edges are in this picture here? Well, any 2 blobs have all possible edges between them. In this picture, it's n over 3 times n over 3 is the number of edges between these 2 things here, right? There are k choose 2 pairs of blobs. It's more illustrative in this picture here, right? There are 10 pairs of classes, right? 10 pairs of classes, and for each pair of classes, there's exactly n over k squared edges between those pairs of classes, right? This has size n over k, and this has size n over k. Number of edges between two sets of size n over k is n over k squared. And if you work this guy out, this becomes k times k minus 1 over 2, and this is k squared on the bottom there. So I'm going to get an n squared over 2, right? N squared here over 2, and then I get k minus 1 over k here. And in a lot of textbooks, you'll see Turan's theorem upper bound written in this form here, but personally, I prefer to rewrite this as this. Same thing here, all right? This to me illustrates better the walk away from full density, or walk towards full density as k gets larger and larger and larger. Of course, that this gets closer and closer to 1 as k gets large is not hard to see either, right? This is a common ratio, but anyway, this one illustrates it better in my opinion. Okay, so this gives us a graph here that has basically as many edges as the upper bound there. Now, this is not exact here, because here, that's not the truth, right? The actual truth, it doesn't have n over k squared. If n is not divisible by k, the best I could put here is I'd have to make a lower estimate. It would actually be something like this: n over k floor squared. And then that, tkn has at least that many edges, and then this is not quite that number there unless n is divisible by k. You got to deal with congruence classes. Like I don't want to do any of that stuff. So the point is, it's about this, which is about the upper bound. Okay. And we'll do away with all these imprecisions in a few moments when we get to the more advanced version of Turan's theorem. Okay. So I want to prove this 2 or 3 times, depending on time here. The first is Turan's actual proof. And it's an easy induction on n. Okay, and let's just remind ourselves what we're trying to prove here. We're just trying to prove this numerical bound. The maximum number of edges in an n-vertex graph without a k+1 clique is this quantity here. So actually what I'm going to do is just say, let G be an n-vertex graph with no k+1 clique, and show that the number of edges is at most this. Okay, G doesn't necessarily have the max. It's just a k+1 free graph, but the one with the max is among them. Okay, all right. And this argument directly mirrors the first inductive proof of Mantel's theorem that we did last time. Okay. So induction on n. So let's just first say let G. Let's say let induction on n. So the base case here, I'm not going to prove it, is when n is at most k. So actually, I think I can put k+1 here if I want. Let's say k. No, you know what? Let's prove it. Base case is n at most k. Then, okay, I didn't think about this in advance, but how many edges can I have in a graph with no k+1 clique if n is at most k? It's at most, it's at most n choose 2. Right? If my graph doesn't have k+1 vertices in it, then I can have all possible edges and still not have a k+1 clique. Right? I don't even have enough vertices to have a k+1 clique. Okay. And what do I want to show? Something is strange here. It's bothering me. I want to show this. So I need to show that this here is at most this thing here. N is at most k. Maybe that'll help me here.
What if we rewrite that 1 minus 1 over k in terms of k minus 1 over k? Because I think we can do some estimates with k squared over 2 or k times k minus 1 over 2.
Yeah, I don't know why this is bugging me here, but what's the order I want here? Okay, I don't know. I'm gonna move on. Okay, like this I don't know, this part's so dumb. Like, I don't know why. I just cannot think straight right now. It's one of these blackboard paralysis, if you know what I'm talking about. So anyway, it's easy to check. Just do some manipulation here. The quantities work out. I don't remember if you want to leave n as k, where you want to leave n is at most k, or leave n as n and whatever, but just check it. Okay, the base case works. Anyway, the statement's nonsensical here anyway, because there's no clique at all. Okay, all right, we'll come back to it if we have time, but okay, so let's let n be greater than k, and assume the statement for graphs on less than n vertices. Okay, just normal induction here. Okay, all right, so now let G be an n vertex graph with no k+1 clique. Okay, where did I write this down? Oh, okay. Yeah, you know what? I see what's going on here. I said something wrong before. So I said that we'll just assume G is any old graph, but actually I'm going to take one that has the maximum number of edges. Okay, we can certainly do that, right? So let be an n vertex graph without a k+1 clique and the max number of edges. Okay, certainly we can do that, right? I mean, there exists some with the maximum, whatever it is, and let's let G be one of those. And the reason for that is the following claim: G contains a k clique. Not a k+1 clique, right? It doesn't have a k+1 clique, but I claim that it has a clique of size 1 smaller than the maximum. Okay, so what's the reason for that? Well, suppose it doesn't have a k clique, right, anywhere in the graph. That means if I take a set of k vertices, there's a missing edge there. Okay, but can I add that edge to the graph? Yeah, I mean, I can add the edge to the graph. I'm not going to create a k+1 clique before I create a k clique, right? The only way I get a k+1 clique is if before I create a k+, well, not create, but have a k+1 clique, and I add an edge to that to get a k+1 clique. But if the k clique is missing, then I can add an edge and get that. So actually, it says something stronger. It says there's tons of k cliques all over the place, but I just need the existence of one k clique. Okay. All right. So let's call that k clique A. All right. So I've got a set of vertices A that's complete, right? All edges are here, and then B is the rest. Okay. Let B be remaining vertices. And then in this picture, I'm going to do similar estimates to Mantel's. In Mantel's theorem, we removed an edge and then looked at the remaining vertices and looked at cross edges and applied induction in here. Okay, so let's estimate the number of edges in this graph here by these three quantities. I've got edges inside of A, edges inside of B, and edges from A to B. Okay, so number of edges in G is at most, how many edges are inside of A? Okay, choose 2. Right, that's this quantity here. How many edges are inside of B? We can apply induction to B, right? B is definitely k+1 clique free because it's just a subgraph of the graph. Cliques don't appear in subgraphs. And it has fewer vertices. It has k fewer vertices. So it has at most 1 minus 1 over k, n minus k over 2 squared. Okay, that's by induction. Right? And then the last thing, now here is where we actually have to think a little bit. The number of cross edges here. Let's imagine the following scenario. So in Mantel's theorem, just to remind you, because it's the same idea, we had an edge here and then a vertex on the other side. Couldn't send edges to both of those vertices because that created a triangle. In this picture, let me do it in green. a vertex in B, what's the one thing it can't do to A? Exactly, Eric, right? B can't send an edge to every single vertex in A, because that would create a k+1 clique, right? That's why I needed A to be a k clique. Otherwise, I can't make that comparison, right? Then I can't say that it has that. So this vertex here sends at most k-1 edges across. So the total number of cross edges is the size of B times k-1 at most, right? What's the size of B? It's n minus k times k-1. Okay. Let me just double check that these are the quantities. That's not written down. Okay, and then I don't want to do the arithmetic here because it's not interesting. But if you work this out, I think you get exactly. But let's say at most, you get exactly what we want. If you just work the thing out here, okay. Just imagine you can multiply out this part here. You got a k choose 2. You got some of this stuff here. The things cancel nicely with this extra part here. Okay. I think it actually is less than or equal to, not exact actually, if you do the arithmetic. I think it doesn't matter, right? Either one is fine. All right. So that ends the proof modulo the base case. But I want to be able to move on because the other proofs are cool. Okay. Yeah, I think I'll only be able to do one more though, because there's an important observation to make here. Okay. So there's actually something pretty cool, some more calculus going on in the background here that can help us make this proof and a more sort of advanced theorem here easier to prove. Okay, so let me restate actually what Turan's theorem really says. Okay, so the unique edge maximal, well, let's not say edge maximal, let me write that differently. N vertex k plus 1 free, that's a plus 1 free graph with max number of edges is the Turan graph TKN. Okay. Let me just emphasize a couple things. Here I use different terminology. Instead of saying no k+1 clique, I said k plus 1 free. That means the same thing, right? So this is no k plus 1 clique. This is much more standard terminology. Okay, just want to show you a different variety here. Okay, so this says more information than before. First of all, it says that the maximum is uniquely achieved by one and only one graph, and it's the Turan graph here. And moreover, this tells us the number of edges. It doesn't give us a numerical quantity, but we know exactly what the Turan graph looks like. We can compute its number of edges. And so this gives an upper bound on every graph that has n vertices and no k+1 clique, right? Because it's like, well, how many does it have? Well, no more than the Turan graph. How many does the Turan graph? Just computed, okay? So this is sort of an elegant way of rewriting the other theorem and not have to deal with approximations anymore. It's like, the answer is whatever that is. And yeah, it's not nicely 1 minus k, 1 minus 1 over k times n squared over 2, but it is what it is, right? It's a number that just, that we can estimate if we want, okay? So this says no graph exceeds the number of edges in this. And moreover, if you have a graph that attains the maximum, that graph is the Turan graph, okay? So something like we saw in Mantel's theorem last time as well, right? If you get n squared over 4, you're the complete bipartite graph that's balanced. Notice that's precisely the statement here for k equals 2. Okay, so I want to prove this version of the theorem because this is what people think of as Turan's theorem. Okay, that the unique maximum is attained by that guy there. And there's a trick about the Turan graph that we can help ourselves out here. Okay, so let's make the following observation before we prove this. So among all n vertex complete k-partite graphs. Okay, it's good Van pointed this out at the beginning because now we don't have to redefine it. So k-partite complete n vertex graph, again, is one with k classes, not necessarily the same size or close, with all edges between pairs of classes. Right? Okay, I'm not going to draw them all in here. So among all of these graphs, actually, let's even modify this slightly more. Yeah, let's say this instead. Among all complete partite graphs, I don't know what K is, without a K plus 1, the Turan graph has the most edges. Okay. Let me prove this in a hand wavy way that can be made fully rigorous and can also be proved using calculus here. But let me explain what's going on here. Okay. So let's think about and even for illustration, let's imagine that K equals 4. Okay. So we're thinking about graphs that have no K5s in them. Okay. So there are lots of graphs that don't have a K5 in them, and there are lots of complete, say, T partite. T is something other than, possibly other than K. So there are lots of these that don't have a K5. For instance, the Turán graph is our goal here. That has 4 classes. Let me redraw it this way. This has 4 classes, right? All of equal size as possible. That doesn't have a K5, and we're hoping to show that's the best, right? But for instance, there's also the bipartite graph with 2 classes that's complete. That doesn't have a K5, certainly. It doesn't even have a K3. You can have a 3 vertex class, 3 vertex one. That doesn't have a K5. And moreover, you could even have a 4 class construction where the classes are not of the same size, right? This also doesn't have a K5. None of these have K5s in them. But what I claim is that this one, the Turán graph, TK, well, this would be T4N. I claim that this one's the best. This one has the most edges among all these examples here. And let me explain to you visually why that would be true. Okay, so let's say, forget the ones of size 2 and 3 for a moment. We'll come back to those in a second. Look at one of size 4 here. Okay, this one here, I claim, has fewer edges than this one here. And let me show you why. It's very simple. Say you have a big class and a small class. What does that mean? It means they differ by more than one vertex, right? In principle, in this graph here, classes can differ by 1 and it's still okay, right? Because there's the round up, round down. But say 2 classes differ by more than 1, so they differ by 2 or greater. What I'm going to do here is take a node from this one and move it there. And look what happens to the number of edges in that picture here. Think about this for a little bit. It goes up, okay? Yes, a number of things happen, right? The edges that went between these 2 classes here, I lost an edge by moving it here, but I gained back this one going to everything here, which it didn't go to before, right? Initially, this had no neighbors in here, and it had some neighbors in here. It lost the neighbors in here, but gained neighbors in here, okay? Modulo the fact that it got moved there, okay? So that's a little bit hand wavy, but it's actually easy to see with a little bit more thought that shifting here to even size classes increases the number of edges. And you just keep doing this until classes are within one of each other. When they're within one of each other, then shifting a node back and forth doesn't have any effect anymore. It just changes the layout, okay? So this says you should do this operation until you get balanced. Now, what about this one here? What if I have 3 classes? Well, what can you do with 3 classes to increase the number of edges and not get a clique of K5? You can just split a class. Let's just split that class in half there and then pretend this is actually 2 classes and add all the edges here. Oh, I want that in black. Add all the edges here and then all the edges from the top new class, right? The top class is the new one. Oh, actually, those are already there. Sorry, right? Those edges are already present between those 2 there. So I just added a bunch of edges between those 2 classes. But what is this picture? It's now one of these pictures here, right? Just pull the top there up, and then you get this picture here. The classes may not be balanced anymore, but then do the balancing trick to go here, okay? And in this one, you can do the same thing. There's 2 classes, split this to get 3 classes, then split that to get 4 classes, then you get 4 classes, then balance, okay? So you have this procedure to arrive at this graph here. And in each step, you only gained edges. So what it says is that, well, that proves the observation here. Again, it's a little bit hand wavy, but actually this can be made fully rigorous here. You don't even actually need to use calculus to do this. Just a little bit of comparison in sizes here. So what this means, this observation, it means the following. It means that if I want to prove this theorem here, if I start with a graph G that has n vertices and is kk plus 1 free and has the maximum number of edges, if I prove that that graph is complete t-partite, then I'm done. I don't even have to prove that it's this one specifically, because as soon as I prove that it's of any of these forms, it has no choice but to be this one, right? Because this one has more than these examples here, and I said it's the edge maximal one. So all I have to show you is that it's complete k-partite. Actually, not even k, complete t-partite, and then the proof is done. Okay, so that'll be my strategy. I have this new thing that helps me prove my theorem. Instead of proving that it's directly this guy here, I'm just going to prove that it's a t-partite complete graph, a complete t-partite graph. And then I can do the shifting and arrive at it has to be the Turan graph, in fact. That's relying on this fact here, that it has the max number of edges, right? Because if it was one of those other ones, I could increase the number of edges, and that should be impossible. Okay, so it has to be TKN. Okay, so we only have time for one of the two proofs of this using this method here. Let me prove Zhikov's proof. Okay, Erdős has a proof, and then there's the Zhikov proof. So this is by Zhikov in 49. We've seen Zhikov before with triangle-free graphs. There was the Zhikov graph, and this proof has a method. It's called symmetrization. This is a lovely, very powerful technique. Let me mention one historical anecdote that's kind of interesting here. So this proof was independent of Turan's theorem. Turan's proof was given in 41. Zhikov was given in 49. They didn't have knowledge of each other. You can maybe guess why. This was in the middle of World War II. Well, not in the middle, but like the years between 41 and 49 were World War II. And Turan's Hungarian, Zhikov's Russian. There just wasn't a lot of journal exchange going on in those years. Zhikov's papers are in Russian, Turan's paper is in Hungarian, the originals there. So this is Zhikov's also, well, he's generally not attributed the theorem at all, but this proof was done without knowledge of the other one. It's sort of an interesting historical anecdote here, okay? And he introduced this technique called symmetrization, and it actually mirrors what we did here. Okay, what we're going to show here is that if my graph has the max number of edges and doesn't have a k plus 1 clique, then it's a complete partite graph. And then it has to be the appropriate Turan graph. Okay. So, and there's no induction here, which is nice. So let's let G be an n vertex, k plus 1, free graph with max number of edges. Okay. All right, so now I'm going to make the following claim that we'll think about, but this is going to be an exercise for you guys. I mean, I'm not going to assign a homework, but it's something I want you to convince yourself of. Okay. So claim, if G is not a complete partite graph. Okay, I don't know why I've been missing this. So the term we say is complete multipartite. When I don't want to give a name to K, I don't know how many classes there are, I just know there's multiple classes. So when I said complete partite graph, this was troubling me. This was not what we say. We say complete multipartite, okay? So instead of t-partite. So if it's not a complete multipartite graph, then there exist vertices x, y, and z such that xz, is an edge, but xy is not. Actually, okay, sorry, I want something. This is if and only if. I want a stronger claim here. So it's not complete multipartite graph, if and only if there exists 3 vertices in this configuration. Okay, what does this configuration look like? X, y, and z, and this edge is present here. Oh, sorry, there. Yeah, and x xy is not, and xz is not. Sorry, all that information there. So it's just this little configuration here. No edge here, no edge here, but there is an edge here, okay? The existence of this substructure means you're not a complete multipartite graph. That's what I want you to prove. I'll explain the other direction, which is the simpler direction. If you're not complete multipartite, sorry, which direction am I going to prove? I don't know which direction I'm going to prove. Okay, I'll prove the reverse. If you are complete multipartite, this thing can't appear. Okay, that's the contrapositive. Let's think about that for a moment. So complete multipartite looks something like this. All edges are here, all edges are here, all edges are here, all edges are here, and here. This configuration can't exist here, right? Because the fact that there's no edge here says x and y are in the same class, right? So x and y are in the same class. And then where's z? Well, z is joined to x by an edge, so it's got to be over here in some different class. But then that says y and z are also joined by an edge, right? And I can't have z in here because then that would say there's no edge among the three there, okay? So if I am complete multipartite, I never see this thing here. But the converse of that is what I want you to think about, is that if I don't see this, then my picture is complete multipartite. I don't know how many classes, but the things are equivalent there, okay? There's actually a whole, there's an equivalence class, equivalence relation type proof of this argument as well, but it's not hard to prove anyway, okay? But this notion is equivalent. The existence of this thing here says you're not complete multipartite, okay? So remember what our goal is. Our goal to prove the theorem is using this to prove that our graph is complete multipartite. So I'm going to pretend that this configuration exists and arrive at a contradiction both times. There'll be two cases. And therefore, this thing doesn't exist. Therefore, I am a complete multipartite graph, okay? By the unproven claim. Okay. So suppose G is not complete multipartite, i.e., I'll not name them, but we have this picture here, x, z, y. Okay. Okay, so the first case is that the degree of x is strictly greater than the degree of y. That might happen. Okay. Let me prove this by picture and then just arguing here. Well, I mean, I have to write something. So if this happens, I'm going to do the following. I'm going to look at x and its neighborhood. This is the neighborhood of x. Z happens to be in that neighborhood. Okay. Now y also has some neighborhood, right? Y has some neighborhood. I don't know, maybe it even shares some vertices. Not necessarily, it doesn't share z, of course, but it might share some other vertices. Okay. What I'm going to do is delete all that and replace y's neighbors with those of x. Okay. So what this says is, in this case, delete edges on y, replace, and join y to n of x. Okay, you guys understand the procedure here? X has some neighbors n of x. If y's neighborhood is strictly smaller than that of x, right? That's the vertices adjacent to. Delete it and update y so that it's adjacent to everything x was adjacent to. Okay. This has two consequences, or one consequence and one non-consequence. What does it do for the number of edges of the graph? I deleted dy edges and added dx edges, so I increased the number of edges. Definitely went up by the number of edges. Should be impossible, right? Unless this creates a clique, a k+1 clique. Can this create a clique though? A new clique? Suppose it created a k+1 clique. That k+1 clique involved the vertex y, because that vertex is the only thing that changed. I mean, other vertices changed, but this is the only one that was updated. This has got to be involved. A k+1 clique looks like the vertex y and some of its neighbors. But if that's a k+1 clique, then that already existed with x in the first place, right? So this procedure increases number of edges, but does not create a k plus 1. But that's a contradiction because my graph was already edge maximal among the k plus 1 things. So this is the first step of a symmetrization, because what am I doing here? I'm making y look more like x. So locally, I'm making the graph look more symmetric, depending on your notion of symmetric. But that's if this happens, right? Suppose that doesn't happen. So case 2 is that dy is greater than or equal to dx, right? And actually, we can also assume that dy is greater than or equal to dz. Okay, because I mean, if you go up to the original picture here, x and y are symmetric. So if dx is bigger than dy, or if dz is bigger than dy, I can perform exactly what happened in case 1, right? And x and y are indistinguishable. I mean, sorry, x and z are indistinguishable from each other from y's perspective. If either of these has bigger degrees than y, do this and get a contradiction. Okay, so in case 2, I'm going to do something similar. So here I've got y, I've got x, and I've got z. Now, x and z are adjacent to each other, and x's neighborhood is over here. This is n of x. And z's neighborhood includes x. It also could include some of the neighbors. So this is n of z. Okay. They may share some neighbors as well, right? There might be, this is an edge. There certainly, in principle, can be triangles. Okay. And then I'm just going to draw it like this, but the neighborhood of y is, say, down here. Of course, the neighborhood of y can intersect these neighborhoods here, but it's immaterial to the proof. So in this case, remove edges on x and on y, and join x and y to the neighborhood of y. So now we do sort of the opposite of the before. I delete all these neighbors and this edge, and now x is joined to all of this, and z is joined to all of this as well. Okay. Notice the edge between x and z was also deleted, right? Because it's adjacent to both. It gets double deleted. No, it just gets deleted once. But okay. So now, what happened here? What can you tell me about the number of edges in this case here? Well, if dy was strictly greater than dx or dz, we definitely increased edges. But even if it equals both of them, we still increased edges. Why? I hinted at it when I made the joke. The double deletion of this edge. This edge is counted once by this degree and again by this degree. And now, in a sense, this edge is being replaced with 2 edges, right? It's now all edges from x and z to this neighborhood, or none of them are replicas of each other. So I lost 1 edge here, but gained 1 for each of them here. So this graph also has more edges. So this graph also has more edges. And can I have a clique? A k plus 1 clique? The argument's the same as before, right? So it's a little bit different because 2 vertices got their degrees changed, but is there any clique in the new graph that contain x and z? No, they don't have an edge between them in the new graph. So any clique either involves x or involves z, and so any new clique looks like this. But if that blue clique were there, it would have been there on y to begin with, which it's not because the graph doesn't have a clique. So, and no k plus 1. Okay, but this is a contradiction again because I just increased the number of edges and still didn't have a clique. So what is both these cases, this is everything, relied on the existence of this thing, and they both led to contradictions. So this is impossible. Okay, and then by our claim here, which still remains unproven, the graph is a complete multipartite graph. And by this part here, if you have a complete multipartite graph with the maximum number of edges, this is, so I would hear multipartite, that has no k plus 1, the biggest one is the Turán graph tkn. And that is what the theorem states there, okay, through this whole chain of argument here. So we got something, this is stronger than the first statement of Turan's theorem we made earlier on with just an edge bound. This is the unique graph here, okay? And it's an upper bound on the number of edges. Okay, so there's something like 10 different proofs of this theorem using all kinds of different techniques. Hopefully I'll have a chance to teach you guys some of them if you have another course with me here or there.